Hello everyone. Today the topic that we are going to discuss is electrostatic potential and capacitance JEE PYQs. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So the first question given below are the two statements. One is labeled as assertion and other is labeled as reason. Assertion: two metallic spheres are charged to the same potential. One of them is hollow and another is solid, and both have the same radii. Solid sphere will have lower charge than the hollow one. Okay, so there are two metallic spheres present having same potential. One of them is hollow and one of them is solid, but both are conductors and both have same radii. And solid sphere will have lower charge than the hollow one. This is the assertion. Okay, so what is the reason? Capacitance of metallic spheres depend on the radii of spheres. So this is the reason. Capacitance of metallic spheres depend on the radii of spheres. So you have to analyze both this assertion and reason and determine and choose one out of these four options. In the light of above statements, choose the correct answer from the options given below. First one is A is true but R is false. Second is A is false but R is true. Third is both A and R are true and R is the correct explanation of A. D is both A and R are true but R is not the correct explanation of A. Okay, so you have to select one out of four options. So I will give you some time. Let's see the solution. So answer is B. A is false but R is true. Okay, so why A is false and R is true? So let's see. The charge Q on the conductor is given by Q equal to CV. So charge is given by Q equal to CV. Okay, so now in assertion, both the spheres have same potential V. Okay, so one of them is hollow and one of them is solid and have the same radii. Okay, and they are saying that solid sphere will have lower charge than hollow one. Let's see, assertion is true or not. So as we know that capacitance of the spherical conductor of radius r is given as this. Okay, C equal to 4 pi epsilon naught r. So you can see that 4 pi and epsilon naught, these are constants. So what is the variable term here? This r, radius. So capacitance depends upon radius of the sphere. Okay, so what was the reason? Capacitance of the metallic sphere depends on the radius of the sphere. Okay, so reason is true. Reason is true because capacitance depends on the radii of the spheres. Now let us see assertion is true or false. So capacitance does not depend on its charge. It only depends on the radius of the conductor according to this relation. Okay, now we can see that Q equal to CV and both the spheres have same potential. Now both the spheres have same radii. It means that both the spheres will have same capacitance because both have same radii na? So capacitance depend on radii only. So if radii is same, so capacitance of both the sphere is same and potential is same, it is given. So it means that charge on both the sphere should be same according to this because capacitance of both the sphere is same and potential on both the sphere is same. So Q should be same. Okay, so but they have written in the assertion that solid sphere will have lower charge than hollow one. This means that this assertion is false, but this reason is true. Okay, therefore assertion is false and reason is true. Okay, so assertion is false because both have same charge on them. So, and reason is true because capacitance of metallic sphere depend on only on the radii of the spheres according to this expression. Okay, I hope you understood. So next question, a parallel plate capacitor of capacitance 2 farad is charged to potential V. Okay, so 2 farad is a very big unit and it is impractical, but in numericals we can also take impractical units, but we just have to solve the question. Okay, the energy stored in the capacitor is E1. The capacitor is now connected to another uncharged identical capacitor in parallel combination. The energy stored in the combination is E2. The ratio E2 by E1. Okay, so initially a parallel plate capacitor of capacitance 2 farad is charged to potential V. Okay, one capacitor is charged. Energy stored in the capacitor is E1. Okay, so we have to determine first. Then now this capacitor is connected to another uncharged identical capacitor. Okay, so similar capacitor, identical and uncharged in parallel combination. So now we are connecting this capacitor with another capacitor which is identical and uncharged in parallel combination. Now energy stored in the combination is E2. So you have to find the ratio. So options are 1:2, 1:4, 2:3 or 2:1. So I will give you some time to think about it. Let's see the correct answer, which is A, 1:2. So let us see what is the solution. So given that capacitance of the capacitor is 2 farad, okay, so energy stored E1 is equal to half CV square. We don't have to put the capacitance because the another capacitor is also identical. Okay, so since it is identical, when we will take the ratio, the capacitance will get cancelled. Okay, so you don't have to put the value for now. Okay, you have to solve till last. If it is required to put the value, then you will put. Okay, so E1 is equal to half CV square. This is the energy stored in the capacitor initially. Okay, put it as equation 1. Now common potential. Now we have connected this capacitor with another identical capacitor in parallel combination. Parallel combination means one capacitor is this, okay, and another capacitor, identical capacitor or uncharged. This is charged by, let's see, this is this capacitor having capacitance C and potential V, and this is charged, and this is uncharged. Similar capacitors, and they are connected in parallel. Okay, one plate of this capacitor is connected to another, and other plate is connected to another of this capacitor. Okay, so when we will connect this both the capacitors, identical capacitors, now there will be transfer of charge from this capacitor to this capacitor. This is charged. Okay, so now there is transfer from this capacitor to this capacitor. Okay, so distribution of charges will start, and after distribution, when static condition is achieved, then these two capacitor will attain some common potential. Okay, so since they are connected in parallel, so they will attain a same potential difference across them, which is called common potential. Okay, so common potential is now, which is given by C1 V1 plus C2 V2 upon C1 plus C2. C1 V1 is for first capacitor, that is charged. So C1 V1 is Q1. Q is equal to CV na? So Q1 equal to C1 V1. That is any charge on capacitor 1. And C2 V2 is Q2, which means charge on capacitor second. So we know that charge on first capacitor is initially CV, Q equal to CV, because its capacitance is C and it is charged to potential V. So CV is the charge, and other was in uncharged. Okay, initially. So first was having charge CV and another having charge 0 upon sum of capacitance of both. Okay, means since they are connected in parallel, so their combination capacitance of combination equivalent capacitance will be simple addition of both the capacitance. Okay, so C1 plus C2, and since they are identical, both having capacitance C, so 2C. Okay, so what is the common potential after solving? V by 2. Now energy stored in the combination is equal to half CV square. Now C is now 2C because they are connected in parallel, so combination will be C plus C. Equivalent capacitance of combination will be simple algebraic sum, which is C plus C, 2C. And V common, that is the common potential across both the capacitors when they are connected in parallel. So common potential square. So common potential was V by 2, so it will become V square by 4. Okay, so it is 2C. So 2 will get cancelled with 4, 2. After solving this, we will get CV square by 4. Put it as equation 2. Now take the ratio. Now E2 by E1. Equation 2 by equation 1, E2 by E1. And after solving, you will get 1 by 2. So the ratio is 1:2. Got it? Okay. Next question. The distance between two plates of capacitor is D and its capacitance is C1. When air is the medium between the plates, if a metal shield of thickness 2D by 3 and of the same area as plate is introduced between the plates, the capacitance of the capacitor becomes C2. The ratio C2 by C1 is. Okay. So now what has been done? Initially capacitor having no dielectric plate. Okay, so its capacitance is C1. Now we have inserted a metal sheet, not dielectric, metal sheet 2D by 3 of thickness. Okay, and of same area as plate is introduced between the plates. Now capacitance becomes C2. The ratio C2 by C1 is. Okay, options are 3:1, 1:1, 4:1 and 2:1. Okay, so I will give you some time to think about it. So let's see the answer. 3:1. First option, A option was correct. 3:1. So let's see the solution. So we know that dielectric constant for metallic sheet. Okay, for metallic sheet, dielectric constant is infinite because metallic sheet will induce charges on its phases in the external electric field. We have seen the behavior of conductor in electric field. It will induce or redistribute the charge in such a way it will totally cancel the external electric field inside. Okay, so it can store a number of charges on its surface and as much charges as we can. Okay, so for metallic sheet, dielectric constant is infinite. Okay, so given thickness of metallic plate T equal to 2D by 3, it is also given. So distance between the plates of the capacitor D. Okay, so now we have discussed in our previous lectures that if the thickness of the dielectric material or any other material that we are inserting between the plates of capacitor having thickness less than the separation between the plates of the capacitor, then how we can modify the derivation? That derivation we have done for the dielectric constant, dielectric fully inserted between the plates. Okay, so how we can modify? We have discussed in the previous lecture in one of the numerical. Okay, so we have to, when we see the electric field between the plates of the capacitor. So when there is a there is no dielectric, the spaces where dielectric is not present or any other material is not present, then we will take E naught electric field. And the space and the thickness for which there is some other material present, we will take E naught by K. Okay, so K is the dielectric constant. So dielectric constant for metallic sheet is now infinity. Okay, so for that type of arrangement, when dielectric medium has thickness less than the separation between the capacitor, then our result for the capacitor is capacitance is given by some different formula. So according to question C1, when there is no dielectric medium, when there is air between the plates of the capacitance, so epsilon naught A upon D. So this is C1. Now this is the formula when dielectric medium of thickness less than the separation of capacitance plates of the capacitor is given. Okay, so then this is the formula. Otherwise, it is Kc naught. If dielectric is fully inserted between the plates, then the capacitance becomes Kc naught. But if it is not fully inserted, then the formula is this. D is the separation, T is the thickness of the dielectric material, T is the thickness, K is the dielectric constant of that material, and epsilon naught A. Okay, so now you have to put all the values in this formula. So epsilon naught A D minus what was T given, thickness of the dielectric plate or metallic sheet, 2D by 3, and K was infinity. For metal it is infinity. Okay, so 1 by infinity is 0, 1 by infinity is 0. So this whole term T by K will become 0. Okay, so it will become 0, equal to, after solving this, we will get 3C1. Okay, so now take the ratio C2 by C1 equal to 3 by 1, or we can say. So what is the ratio? 3:1. Okay, I hope you understood. A capacitor of capacitance C is charged to a potential V. Okay, a capacitor of capacitance C is charged to a potential V. The flux of the electric field through a closed surface enclosing the positive plate of the capacitor. If any closed surface is enclosing a positive plate of the capacitor, what is the flux through it? Okay, so we have to calculate this thing. So the options are CV by 2 epsilon naught, 0, 2 CV by epsilon naught, or CV by epsilon naught. So I will give you some time. So let's see the answer. D is the correct option. CV by epsilon naught. So let's see the solution. Okay, so this is type of arrangement is there. There is a battery which is charging this capacitor, and this capacitor, this plate having positive charge and this plate is having negative charge. Okay, and same charge but different polarity, means Q charge on this plate, Q charge on this plate, but plus Q on this plate, minus Q on this plate. Okay, so we know that we say that charge on the capacitor is Q. We will only take charge on the positive plate. Okay, we don't take the net charge is 0. We only take the charge which is present on the positive plate. We can say charge on the capacitor is Q. Okay, so the flux of the electric field through a closed surface enclosing a positive plate of the capacitor is CV by epsilon naught. This is the answer. So now we can see, according to Gauss law, the electric flux through any closed surface, if any closed surface is there and enclosing this positive plate of this capacitor like this, okay, so flux through it will be Q enclosed by epsilon naught. Okay, so this surface is enclosing positive plate of capacitor having charge plus Q. Okay, so this flux will be equal to Q enclosed, that is Q plus Q upon epsilon naught. Okay, so charge on the capacitor is given by, so charge on the capacitor Q, that is on positive plate, can be given by Q equal to CV. This is the formula. Charge on the capacitor is given by Q equal to CV, and this charge is equal to the charge on the positive plate. Okay, so Q equal to CV. So that charge is enclosed by the closed surface. So put this Q on this Q enclosed and equal to CV. So it will become Q flux through that closed surface will become CV upon epsilon. Okay, simple. Let's move on to the next question. A parallel plate capacitor has plate area 40 centimeter square and plate separation 2 millimeter. The separation between the plates is filled with a dielectric medium of thickness 1 millimeter and dielectric constant 5. The capacitance of the system is. Okay, so now there is a capacitor having 40 centimeter square plate area, 2 millimeter separation. Area between the plate is filled with dielectric medium of thickness 1 millimeter. Now, thickness of the dielectric medium is less than the separation between the plates. Now again, that formula which we used in the previous question, and dielectric constant 5. Capacitance of the system is 24 epsilon naught farad, 3 by 10 epsilon naught farad, 10 by 3 epsilon naught farad, or 10 epsilon naught farad. So I will give you some time to think about it. Okay, so C option is the correct option, 10 by 3 epsilon naught farad. Okay, so let's see the solution. So given A is equal to 40 centimeter square, which is equal to 4 into 10 raised to power minus 3 meter square. Okay, after changing the units. Okay, so converting it into SI units. So 1 centimeter square is 10 raised to power minus 4 meter square. Okay, so 10 raised to power minus 4 meter square, and there is 40. So after converting it to 4, it will become 10 raised to power minus 3. And D is 2 millimeter, which is equal to 2 into 10 raised to power minus 3 meter. Okay. Thickness is 1 millimeter, which is 1 into 10 raised to power minus 3 meter, and dielectric constant is 5. So capacitance when dielectric is inserted is given by this formula. Again, this formula. When separation between the plates is different from the thickness of the dielectric constant. Okay, dielectric material. So D minus T plus T by K. So K is 5 here, T is 1 millimeter here, D is 2 millimeter here. Okay, and epsilon naught, you know the value, constant, and area is also given. Okay, now put this value. So we don't have to put epsilon naught. Okay, so they have maintained the epsilon naught value as it is in the options also. So we don't have to put epsilon naught value. So epsilon naught into 4 into 10 raised to the minus 3 upon 2 into 10 raised to the minus 3 minus 1 into 10 raised to the minus 3 plus 1 into 10 raised to the minus 3 upon 5. Okay, which is equal to, after solving, 4 epsilon naught into 10 raised to the minus 3, 10 raised to the minus 3, 1 plus 1 by 5. After taking common 10 raised to power minus 3 from all. Okay, we will get this type of thing. And after solving this, we will get 4 epsilon naught into 5 by 6, which is equal to 10 epsilon naught by 3 farad. So this is the answer. Okay, I hope you understood. In the network shown below, the charge accumulated in the capacitor is steady. Okay, steady state will be. So we have to, this circuit is given. So we have to find the charge accumulated on this capacitor in steady state. Okay, so options are 12 microcoulomb, 4.8 microcoulomb, 7.2 microcoulomb, and 10.3 microcoulomb. Okay, I will give you some time to think about it. So let's see what is the correct option. C is the correct option, 7.2 microcoulomb. So let's see the solution. So circuit is given like this. Okay. So this is the battery. So this is the I current flowing from it. And at this junction, this I is being divided into I1 and I2. I2 is going from this circuit and I1 is going from this circuit. Okay. And now you can see that in steady state, when capacitor becomes fully charged, it will block the DC current. DC current means direct. We will see the detailed part of DC and alternating current in our upcoming chapter 7. Okay. So this is the capacitor. Okay. So it will, in steady state, it will block the DC. It will prevent the flow of current through this branch of the circuit. Okay. So it means I2 becomes 0. So in steady state, no current will pass through the capacitor. Hence, capacitor will act as an open switch. Okay, it will act as an open switch. It will block the current through this circuit. Okay, so I2 will be 0. Since no current is flowing through that branch, so this resistor will not be considered in the circuit. Okay, because there is no current flowing through it. There is no potential difference across this resistor. So it will not be considered. It will be cancelled from the circuit. It has no contribution in the circuit. So now this resistor and this resistor is being considered. And since no current is flowing through it, now this is the circuit. The current flowing through this and returning to this in this path like this, from this and returning via this path. Okay, so this path is blocked by this capacitor. Okay, now current is flowing. So these 4 ohm resistor and 6 ohm resistor will be in series. Okay, so after adding them for equivalent resistance in series, we used to find with simple algebraic sum. Okay, 4 plus 6, 10 ohm. And what is the current? We want to find the current. So V by R, 3 by 10. Okay, so current is 10. This I current. This I1 is equal to I. Okay, so this I1 is returning. I2 becomes 0. So 3 by 10 is the current. Okay, so let's see. So this is the circuit. Now current will be 3 upon 6 plus 4. 6 plus 4. This resistor having no potential difference across it because no current is flowing through it. 3 by 10 ampere is the current. This I current. I1 or I is equal to I1. Okay, because I2 is 0. So I1 current is 3 by 10 ampere. Okay, so potential difference across this 6 ohm resistor. Potential difference across this 6 ohm resistor is 0 because no current is flowing through it. This 6 ohm resistor across this 6 ohm resistor is 6 into 10, 3 by 10. So what is the potential here? 1.8 volt. So 1.8 volt potential difference is across this 6 ohm resistor. Since this 6 ohm resistor is connected in parallel to this branch and to this branch, so potential difference across all the branches will be same because they are connected in parallel. Current will be 0 here, but potential difference is still there. Okay, potential difference across this 6 ohm resistance is 0, but potential difference across this 4 microfarad capacitor is similar to that 6 ohm resistor, which is at the lowermost branch. So 1.8 volt. So capacitor will have same potential since it is connected in parallel. Okay, this 6 ohm resistor will not having any potential difference across it because no current is flowing through it. Okay, so capacitor will have same potential. So charge Q equal to CV. Okay, so capacitance of this capacitor is 4 microfarad and 1.8 volt is the potential difference across it. So capacitance of this capacitor will be 7.2 microcoulomb. Since this 4 is microfarad, that's why it is microcoulomb. Okay, got it? Let's move on to the next question. Voltage rating of a parallel plate capacitor is 500 volt. Its dielectric can withstand a maximum electric field of 10 raised to power 6 volt per meter. The plate area is 10 raised to power minus 4 meter square. What is the dielectric constant if the capacitance is 15 picofarad? Okay, epsilon naught is given 8.86 into 10 raised to power minus 12 coulomb square per Newton meter square. Okay, so we know that it is the maximum limit that a dielectric can withstand. Okay, so this is the breakdown electric field, 10 raised to power 6 volt per meter, and the plate's area is this, and voltage rating of parallel plate capacitor is 500 volt, and this is the capacitor. And what we have to find dielectric constant. Options are 3.8, 8.5, 4.5 or 6.2. Okay, so I will give you some time to think about it. So answer will be B, 8.5. So let's see the solution. So this is the type of arrangement. This is capacitor and this is dielectric medium that is inserted between the plates, and this battery is connected in this way. So this is the D, separation between the plates of the capacitor. A is equal to A. As we know, capacitance of capacitor filled with the dielectric medium is given by this formula. If it is fully inserted, okay, it is fully inserted. So C equal to epsilon naught Ka upon D. Okay, so A epsilon naught D will be C naught K. Okay, so epsilon naught Ka upon D. Put it as first equation. Now, magnitude of the potential difference between the plates is E equal to V by D. We know that electric field is equal to V by V is the potential difference between the plates. D is equal to separation between the plates. Okay, so we know that E is equal to minus dV by dr. Okay, so that is also, what is that? For small variations, okay, or for non-uniform electric field, okay, also for non-uniformity. Okay, so for uniform, if the electric field is same in that place between the plates, so we can use that V by D. Okay, if electric field is not uniform, then we will use D minus dV by dr. Okay, differentiation way. But here this is not in the form of non-uniform. Potential difference is also constant between the plates, and electric field will also be constant between the plates. So we can use this without differentiation, V by D. Okay, so V is the potential difference between the plates and D is the separation between the plates. So from here D will be equal to V by E. Put it as equation 2, and this equation 2 value of D will be put in the equation 1. So by combining both equation 1 and 2, after putting the value of this D in equation 1, we will get this. Okay, so in equation 1, which is equal to C equal to epsilon naught A K upon D, put the value of D there, and for K, we will get this CV upon epsilon naught AE. Put this equation as 3. So now C is given 15 picofarad, which is 15 to 10 to the power minus 12 farad. Voltage V is given 500 volt. Electric field maximum limit is also given 10 to the power 6 volt per meter. And area is also given 10 to the power minus 4 meter square. Epsilon naught value is also given. So put these values, substituting the values in equation 3, we get K equal to 15 into 10 to the power minus 12 into 500 upon 8.85 into 10 to the power minus 12 into 10 to the power minus 4 into 10 to the power minus 10 to the power 6, which will, after solving, we will get 8.47, which is nearly equal to 8.5, which is our option. Okay, got it? So next question, a parallel plate capacitor has 1 microfarad capacitance. One of its plates is given 2 microcoulomb charge and another plate is given 4 microcoulomb charge. The potential difference developed across the capacitor is, okay, one plate is given 2 microcoulomb charge, another is plate 4 microcoulomb charge. Now condition as reversed. We have learned that one plate, both the plates have same charge but different polarities. Now this can be the case that both the plates have same polarity of charge or different charge, but one having greater charge, one having lower charge. Okay, so the plate which is at greater charge will be at greater potential and another plate will be at lower potential. Okay, so this plate will be considered as more positive and this is less positive. Okay, so this will be considered as first plate, this will be considered as second plate. Okay, in the place of negative plate, we will consider the plate with less positive value. Okay, with lesser potential, and the plate with greater potential will take the having greater positive charge. Okay, so this capacitor is having 1 microfarad capacitance. The potential difference developed across the capacitor is, options are 1 volt, 5 volt, 2 volt or 3 volt. Okay, I will give you some time to think about it. So answer is option A, 1 volt. So let's see the solution. Potential difference between the plates V1 minus V2. This is the potential difference. V1 is the potential of positive plate, we can see. But here both the plates are positive. So plate with greater potential. Okay, plate having more positive charge. So 4 microcoulomb. So V1 minus V2. And electric field due to that plate with more positive charge minus electric field due to plate with less positive charge into D. This is the formula. We can find the potential difference equal to ED. This is the relation of V equal to ED. So potential difference equal to difference in the electric fields and E1 minus E2. What is this? Net electric field between the plates of the capacitor. Okay. After subtracting both the electric fields due to individual plates, we will get the net electric field between the plates of the capacitor into D, which is the separation between the parallel plates of the capacitor. Okay, so E1 and E2 are the electric fields due to each plate. D is the distance between the plates. Substitute electric fields. Now substitute the electric fields. We know that electric field due to a plane sheet is given by sigma by 2 epsilon naught. Okay, so E1 will be sigma 1 by 2 epsilon naught. Sigma 1 will be surface charge density of the first plate and E2 is equal to sigma 2 by 2 epsilon naught. Sigma 2 will be the surface charge density of another plate, of the second plate, which is at lower potential, having less positive charge. So V1 minus V2 will be equal to sigma 1 upon 2 epsilon naught minus sigma 2 upon 2 epsilon naught into D. Okay, so we know that what is sigma 1? Surface charge density, which is Q1 upon A. Sigma 2 is equal to Q2 upon A. Okay, so Q1 is the more positive charge, Q2 is the less positive charge. Okay, so put these values in this. So it will become V1 minus V2 equal to Q1 D upon 2 epsilon A epsilon naught minus Q2 D upon 2 A epsilon naught equal to Q1 minus Q2 upon 2 epsilon naught into D. Now we know that capacitance is equal to epsilon naught A upon D when there is air between its plates. So A epsilon naught will become equal to CD. Okay, So V1 minus V2 equal to Q1 minus Q2 upon 2C. Okay, after putting the value, according to this relation, epsilon naught A upon D. So epsilon naught A upon D can be written as C. So this can be written in this equation. So Q1 minus Q2 upon 2C. Okay, so now put the values. Q1 is more positive charge 4 minus Q2 2. 4 minus 2 upon 2, capacitance is 1 microfarad 1. Okay, charges are in micro coulomb. Capacitance is also in micro. So micro will get cancelled from numerator and denominator. Okay, so we will get 2 by 2 equal to 1 volt. Understood? So this is the question. Next question. In the circuit shown in the figure, the total charge is 750 microcoulomb and the voltage across the capacitor C2 is 20 volt. Then the charge on the capacitor C2 is. Okay. So total charge in the circuit is 750 microcoulomb and capacitor C2 voltage across C2 is 20 volt across this. Means if the voltage across C2 is 20 volt, it means voltage across C3 is also 20 volt because they are connected in parallel. So voltage across both these capacitors C2 and C3 will be 20 volt. Then the charge on the capacitor C2. We have to find the charge on the capacitor C2. Options are 450 microcoulomb, 590 microcoulomb, 160 microcoulomb or 650 microcoulomb. Okay. So I will give you some time. In the circuit shown in the figure, the total charge is 750 microcoulomb and the voltage across is 20 volt. Okay, so let's see the solution. So answer correct option is B, 590 microcoulomb. Solution is, so let's see. This is the voltage 20 volt across both the capacitors. It is given that across C2 20 volt, but they are connected in parallel. So voltage across both the capacitor will be 20 volt. And this is the V1 voltage across this capacitor. We don't know. Okay, so C1 is 5 microfarad, C3 is 8 microfarad. We have to find the charge on this capacitor C2. Okay, so how will we find? So charge, we know that charge in the circuit series will be same. Okay, so charge on this C1 will be this 750 microcoulomb. Charge in the series remains same. Okay, so this C1 and combination of this C2 and C3 is in series. Combination, listen carefully, combination of C2 and C3 and this C1 are in series. Okay, so charge on C1 will be 750 microcoulomb and charge on this combination will be 750 microcoulomb. Means charge on both the capacitor C2 and C3 will be 750 microcoulomb. Okay, since they are connected in parallel, charge will be divided. But for the combination, it is total 750 microcoulomb. So charge on this Q2, this C2, that is Q2, and charge on this capacitor C3, which is Q3. The sum of both the charges will be equal to 750 microcoulomb. Because in series, charge remains same. Okay, so now we will find the charge on this C3 because we know that potential difference across it is 20 volt and also know its capacitance. Okay, so after putting the value C3 equal to 8 microfarad and V2 equal to 20 volt, we will get 160 microcoulomb. That is the charge on this capacitor C3. Okay, so we know that sum of charges on both these capacitors is 750 microcoulomb. So then charge on Q2 will be Q2 plus Q3 is, we have found that Q3 is 160 microcoulomb, total charge is 750. So Q2 will be 590 microcoulomb. Understood? So this question, a parallel plate capacitor with plates of area 1 meter square each are at separation of 0.1 meter. If the electric field between the plates is 100 Newton per coulomb, the magnitude of the charge on each plate is. Okay, so take epsilon naught as 8.85 into 10 to the power minus 12 coulomb square per Newton meter square. So parallel plate capacitor is there, area between its plates is 1 meter square, separation is 0.1 meter, and electric field between the plates is 100 Newton per coulomb. Magnitude of charge on each plate we have to find. So option A is 7.85 into 10 to the power minus 10 coulomb. Option B is 6.85 into 10 to the power minus 10 coulomb. Option C is 8.85 into 10 to the power minus 10 coulomb. And option D is 9.85 into 10 to the power minus 10 coulomb. So I will give you some time. So let's see what is the correct option is C. 8.85 into 10 to the power minus 10 coulomb. So let's see the solution. Q is the charge on each plate. Okay. Then Q equal to CV. We know that Q equal to CV. C is equal to epsilon naught A upon D and V is equal to ED. Okay, we know that V equal to ED, electric field into separation between the plates. So this D and this D will cancel out. So it will become epsilon naught AE. Okay, epsilon naught value is given, A value is given, E value is given. Okay, so we can find the charge. So area is given 1 meter square, electric field is given 100 Newton per coulomb, epsilon naught value is given. Okay, so by substituting given values, we get Q equal to 8.85 into 10 to the power minus 12. This is the epsilon naught into area is 1 meter square. And what is the electric field? 100 Newton per coulomb. After putting these values, we will get 8.85 into 10 to the power minus 10. Okay. So next question, a combination of capacitor is set up as shown in the figure. The magnitude of the electric field due to point charge Q having a charge equal to the sum of charges on the 4 microfarad and 9 microfarad capacitor at a point distance 30 meter from it would be equal to. Okay, so this type of network is shown. Okay, so magnitude of electric field due to point charge Q. So we have a point charge Q and this Q is equal to the charge, the sum of charge on both these capacitors, 9 microfarad and 4 microfarad. Okay, so the sum of charges on both these capacitors, 4 microfarad and 9 microfarad, this is the magnitude of this Q. Q is equal to the sum of the charges on capacitor 9 microfarad and 4 microfarad. And we have to find the electric field due to this point charge. There is some point charge placed. So we have to find the electric field at a distance 30 meters from it. Okay, so why this network is shown if point charge is given? Okay, so there is some point charge from which we have to find the electric field at a distance of 30 meters. But why this network is shown? The magnitude of this point charge is equal to the charge on this 9 microfarad plus this 4 microfarad capacitor. So firstly, we have to find the charges on this two capacitors. Then the sum of these charges will be equal to Q. Then we can find the electric field. Okay, so your options are 420 Newton per coulomb, 480 Newton per coulomb, 240 Newton per coulomb, and 360 Newton per coulomb. So I will give you some time to think about it. Okay, so correct option is A, 420 Newton per coulomb. So let's see the solution. So firstly, we have to take the resultant to find the charge in this whole branch. Okay, so resultant of this 3 microfarad and 9 microfarad capacitor, since they are in parallel, so their resultant, their equivalent capacitance of combination will be algebraic sum of both the capacitance. So 3 plus 9, 12 microfarad. So resultant of this 3 microfarad, okay, equivalent capacitance of this combination will be 12 microfarad. Okay, now resultant of this 4 microfarad and 12. So the combination equivalent capacitance of this combination 12 microfarad is there. Okay, now 4 microfarad and this combination is in series. So equivalent capacitance of this series combination will be having 4 microfarad capacitor, and the capacitance of this combination is 12 microfarad. And now resultant of these both the capacitance will be equal to, since they are in series. So what is the formula? 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Okay. So after rearranging, we will get C1 plus C2 upon C1 C2. And what is the equivalent capacitance become? So this is the thing. So 1 by C equal to 1 by C1 plus 1 by C2. Okay, which will become C1 plus C2 upon C1 C2. So this C will become C1 C2 upon C1 plus C2. Okay, so this thing is given. So C1 is 4 microfarad and C2 is combination capacitance of this combination 12. So C1 into C2 upon C1 plus C2. Got it? Equal to 3 microfarad. Okay. So Q equal to CV. Okay. Which is equal to 3 into 8. So now charge in this branch. So charge in this branch. So equivalent capacitance of this whole combination, this 3 microfarad, 9 and 4 microfarad, capacitance came out to be 3 microfarad. Okay. So Q equal to CV now. So 3 microfarad into potential, since this 2 microfarad and this combination of 3 capacitors are in parallel, so potential difference across these two branches will be 8 volt. So potential across this branch will be 8 volt, and 3 into 8, 24 microcoulomb is the charge in this branch. Whole branch. Charge is 24 microcoulomb. Since charge remains same in the series, so charge 24 microcoulomb will be on 4 microfarad, and this 24 microcoulomb will be on the combination of these two capacitors. Okay, this 24 microcoulomb is on this 4 microfarad capacitor and the combination of these two capacitors, because charge remains same in the series. Okay, now this 24 microcoulomb distributes in direct ratio of capacity between 3 microfarad and 9 microfarad. Now, since they are in parallel, so charge will be distributed. This 24 microcoulomb will be distributed among these two capacitors in direct ratio. Means if this capacitor is having capacitance less than this, the capacitor having less capacitance will get less charge. The capacitance with greater capacitance will get greater charge when they are in parallel combination. Okay, so indirect ratio of capacity means according to capacity. If capacity is less, charge accumulated will be less. Therefore, charge on 9 microfarad capacitor. So these are in direct ratio. Means if the charge, we have to find the charge on this 9 microfarad capacitor, we have to do this. Capacitance of this capacitor upon the net capacitance of the combination. Okay, so combination is, in combination there are two capacitors, which is one is 3 microfarad capacitor, second is 9 microfarad. So in equivalent capacitance 3 plus 9 net capacitance. Okay, in denominator. In numerator, the capacitance for which, the capacitor for which we have to find the charge. Okay, so 9 upon 3 plus 9 into total charge is 24 microcoulomb on both these capacitors. Okay, got it? I will explain again. So charge on this 9 microfarad capacitor will be equal to the capacitance of that capacitor upon the net capacitance of the combination. Okay, so in combination, there are two capacitors of 3 microfarad, 9 microfarad capacitance. So into net charge on both these capacitors. So net charge is 24. So charge on this 9 microfarad capacitor will be 8 microcoulomb. Okay, so now the sum of charges. We have to find the sum of charges on 4 microfarad and 9 microfarad. Okay, so on 4 microfarad, charge is 24 microcoulomb. That is the charge in the series. Okay, charge will remain same in the series. So on 4 microfarad, charge will be 24 microcoulomb. And on 9 microfarad, we found 18 microcoulomb, which is equal to 42 microcoulomb. Okay, and this 42 microcoulomb is the magnitude of that point charge, Q. Got it? So now, electric field due to this point charge at a distance 30 meter from it, kq by r square. Putting this value, k is 9 into 10 power 9 into magnitude of the charge is 42 microcoulomb, which is 42 into 10 power minus 6 upon 30 meter square. Okay, which is equal to 420 Newton per coulomb. Got it? So thank you. I hope you understood and enjoyed the session.